Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
To have Professor Andrey here with us. He's visiting us for the entire week. He's currently a professor at the University of Freiburg, and before that he was a professor at Saarbrücken, and he also spent 1 year here at MSR on sabbatical. Professor Podolsky has done many well-known pieces of work on static analysis of program verification, and today he's going to tell us about some of his recent work.
Thank you, Shaz. So this is joint work with Andrey Rybalchenko and Thomas Wies, and Thomas is now an intern here for a couple of months. And I'm glad he's here because there are some technical points that I always have trouble getting into my mind, and then he will assist me. So this work is about termination analysis of heap manipulating programs, and the major application area is low-level operating systems code. An operating system is not supposed to terminate. In fact, it is supposed to have ongoing behavior, but yet the subroutines must terminate so that the operating system remains responsive. And so it does not matter so much what this excerpt here does. By the way, this is part of the Vamos operating system, which was built by another student intern from Freiburg, Stefan Maus, as part of the verification project. So some people are involved in the very soft project. So that's a project on verification, and some people here from Microsoft are involved in this project. So you have this call of a procedure that is supposed to go through a list and remove one of the entries in this list, the one that is looking for. So yeah, I killed the procedure call. So here you have a while loop that that terminates if either it has reached the end of the list or it has found the element. And when it has removed the process from the list, then it is supposed to do some cleaning. And if the process had the highest priority, then it needs to go once more through the list. So there is another while, yeah, here. And so go through the list after the other process has been removed. And so so you see that the termination property will not hold in general. You need that the list is acyclic. Otherwise, if it does not contain the element, it will loop forever. And so what happens? It goes through the list until it has found the element, and then it removes it. And now it looks, in the case where the process had the maximal priority, it goes through the list and the list where the element has been removed. So so I said this before, the outer loop diverges if the ready list is cyclic and the process is not contained in the list. So we need a precondition, namely that initially this ready list is acyclic. So this is to show that in order to reason about termination, you need preconditions that say something about the shape of the heap. And here by shape, I mean shape in a large sense, and everything that tells us about aliasing, about reachability, about separation of regions, and about sharing. And moreover, in order to show the termination of the inner loop, you need to have the similar kind of information, but this time in the form of an invariant. So it is well known that in order to reason about termination, you need invariants. You need to compute invariants as auxiliary assertions, and in this case here we need the invariant that also after the removal the ready list is still acyclic. Okay, so I use the term heap assumption to refer about assertions on the heap, the ones that I mentioned before. And we need these heap assumptions in invariants, and we need them as preconditions. Now, it is tedious and perhaps also hard to state those preconditions, to find the right preconditions that make that the termination property holds. And so the question that we asked ourselves is, can we compute those preconditions? And this is what the talk is about. So I will present an algorithm that we apply to heap manipulating programs. So sometimes I call them heap programs for short. And the algorithm infers a complete set of preconditions, complete in a sense that I will specify later. And then for these derived preconditions, it proves termination. And what are the main ingredients of this algorithm? So there are two steps. The first step is an abstraction, and the abstraction is not by predicate abstraction or transition predicate abstraction in the way that we are used to, but by a source-to-source transformation that is linear in the number of statements of the program. In fact, it does a translation statement to statement into a program that we call a measure program. And I will explain what that is. And this abstraction here, since it's so cheap, we expect that it will be too coarse to allow us to prove the termination. So we will refine the abstraction by calling shape analysis, and we will call the shape analysis in an economical fashion. And in fact, we will not only refine the abstraction, but since we want to compute a precondition, we will, if needed, refine the precondition. Okay, so in the good case, where the program is correct with respect to termination for every input, the precondition that we want to derive is true, and then we will refine the abstraction until we have shown this. Or in the other case, where for no input the program terminates, in this case the precondition would be false. So these are the two extreme cases, and neither of them will apply in practice. Okay, so this work fills a gap in 2 lines of recent work on the analysis of heap programs. So there has recently been work to prove termination of heap manipulating programs under given preconditions. So there is a work by Josh Burdan, Byron Cook, and others. And there the preconditions are given in terms of separation logic formula. And those formula give, in fact, very restrictive preconditions that include certain forms of alias and require certain forms of separation between regions. And then there is work by Ahmed Bourjani and others, where they translate a heap program into an equivalent program, equivalent in the sense that it has the same termination behavior. And this program is over integers only, and then they show that for the programs that result from this, termination is decidable. So in fact, and this is perhaps a surprising result, for programs where the termination depends only on the shape, so on assumptions on the heap, the termination is decidable. Okay, and there is also work on inferring preconditions. So these algorithms apply again to heap programs, but not for termination, but for memory safety. So this is work by Hong-Seok Hyun and Peter Hearn and others.
About this comment you made that if the termination depends only on the heap property, then termination is decidable. Is that not true general safety property? Is that true only for termination?
It should. Thomas, do you know?
I think it's, I mean, the decidability you only get for simple program, for simple loops.
For sing. Okay. And then it's also for safety. Okay, but thanks for the rectification. Yeah. So it's only for a subclass of programs, namely with simple loops. The algorithm applies to the full class, but the termination guarantee of the analysis we get only for this class of programs that don't have simple loops. Okay. So when I say the termination depends only on the shape, then it does not depend on the contents of the cells. Okay, and then, so I said that this work fills a gap in 2 lines of recent work, and there are 2 other lines of recent work, and there we use the results, and we use them directly, namely by calling the corresponding algorithms as subroutines of our algorithms. So one of these lines of work is on shape analysis. So shape analysis infers invariants, usually at all program points, and that is very expensive. This is known to be very expensive. But we have recent work, so one is by Thomas Wies, and another one is by Dirk Bayer and Tom Hensinger and others, that shows that if you call shape analysis not to infer invariants at all program points, but if they are targeted towards checking one specific invariant in one program point, then the shape analysis can be adapted, and then it is more economical than applying it to infer information about the program at all program points. Okay, and the other line of work is on termination analysis. So you have heard probably talks by Byron Cook on our work on Terminator, together with Andrey Rybalchenko. And there is a long tradition of work that is now mature and that has produced several tools. And all this work on tools that analyze termination of programs, all this work is intimately linked to integers. So I mentioned before the work on termination of heap manipulating programs, but in both cases, the termination analysis works by a translation to integer programs. Okay, so there are 2 parts of this talk. There are 2 parts of the technical part, and then I will give an outline of the remainder of the part, of the remainder of the talk. So in the next step is to describe this source-to-source transformation of a heap manipulating program into the measure program, and this step implements our abstraction. And after that, I will explain how the algorithm calls shape analysis on demand in order to refine either the abstraction or the precondition. Okay, so in the following, the notion of the measure will be crucial. So given 2 variables that refer to cells in the heap, for example, x and y, m of xy measures the distance through dereference chains between these 2 cells. Okay, so the distance between x and y is 3. The difference between y and x is infinite, since x cannot be reached from y. And the difference between x and z is 0. Distance, sorry. Okay, so this is what you will, this m of xy, this is what you will see in the next half an hour over and over again. Okay, so these assertions about the measure is an integer, and it is a positive integer, except that it can take also the value infinite, plus infinite. So we have assertions on these measures, and these assertions are evaluated in a state of the heap program. Okay, so here you have 3 assertions that all evaluate to true. And so these assertions, they describe the shape, because when you say that the measure of xy is smaller than infinite, then this means that from x you can reach y infinitely many steps. If you say that it's greater than 0, it means that x and y don't form an alias. So you can express all this information on separation of regions, reachability, sharing, and aliasing by these assertions on the measures, about the integer values of these measures. And we came to these measure assertions by starting from separation logic formula. So we still need to investigate what is exactly the relation between separation logic formula and these measure assertions, and I suspect that the expressiveness is comparable. Now, these measure assertions are what we will use to express preconditions and what we will use to express invariants. Right? This is how we state our property on the shape from now on. Okay, so one thing we can do is replacing the expressions over pointer variables by measure assertions. Okay, so for the analysis, the termination behavior of these two programs is the same. Yeah, so instead of writing while x is different from y, we write while the measure of xy is greater than 0. And so if x goes towards y, then the termination will hold once the measure between x and y is equal to 0. Okay, so one idea is that instead of using these measures m of xy as expressions that we evaluate on the Heap program, to use them as integer variables. And that means that we will not only have the expressions in the while conditions, so this would now be the comparison between an integer variable and 0, but update all these measures. So each time we have an update statement in the Heap program, we annotate it by an update of all the measures according to the size effect of the statement. So when you update x, you must not only change the measure of x to y, so I will show an example next, but there may be many side effects depending on whether there is a cycle, on whether z lies on the list between x and y, and so on.
When you have a question, when you write m of x comma y, do you think of x and y as addresses, or do you think of them as variable names?
So so here, I think of them as variable names. Yeah? But now, these expressions here, m of x comma y, they have two lives, or two meanings. So one is really as an expression that evaluates in the state of a Heap program, and one is an integer variable. So I should perhaps write x and y as a subscript to make clear that these are not variables. Yeah? Yes, I should have said this. So this is one assumption for now, but I will come to that later. We are looking at singly linked lists, and we have only one field. So I don't need to index the measure by the field. Okay, so more questions, because this is really the crucial point, that I can use these measures here as expressions evaluated on states in the Heap programs and as integer variables. Okay, and then once I have this annotation, then one simple idea is to just keep only the annotation and get rid of the pointers. And in that way, I have done a transformation from a heap manipulating program to an integer program. So in this program we have these measure assertions, which are just assertions on integer variables in the integer program, in the measure program. And we have all the updates on these variables here. Okay, so I will now explain how I translate each operation in the heap program by an operation in the measure program where I update this measure. And what I want to achieve is that the update of the measure is really not losing any precision. So if I have a transition from a state q to a state q prime and I evaluate in the new state the measure, then this should be exactly the value of the expression in the old state. Yeah? This is how I will do my translation. And now, for example, if I update z to y, what does the measure update look like? Okay, so I need to find out what is the difference between x and z after the update. Okay, this is very easy because I know what the difference between the distance between x and y is, and so the measure of xz is exactly updated to the measure of xy. So that's an easy one, but what is more involved is when you have a destructive update. Okay, so this is the update, the next field of x is updated by y. So we distinguish now several cases, so we do a case split. So we wonder if we have two cells S and T, I mean two expressions whose value are these addresses, how should I update their value? Okay, so the first case is where, so what does this mean? That the measure of ST is smaller or equal to the measure of SX. Where we use this measure assertion, remember these measure assertions express as information about the heap, to account for one of two situations. Either I reach T from S without hitting T, or both of these values here are infinite, so from S I reach neither T nor X. So there should be, I'm going too fast. Okay, so in this case, the measure of ST is simply unchanged by the update, by the destructive update of X, right? I mean, I don't reach X before I reach T, so it does not matter. Now, I really must concentrate myself on these. They're really tough, I mean, for me still. So what if you either don't reach T from S, or you reach it after having reached X? Okay, so in this case we are in trouble, right? Because now the update of X matters for measuring the distance between S and T. So I must now distinguish yet more cases. So either the T is not reachable from Y, and I either don't reach the T from Y, or I reach it before I reach the X from Y. Okay, so this is this case here. And in this case, this is still relatively pleasant. I just need to take the distance between S of X and add the distance from Y to T, and then add 1 because I have added this link here from X to Y. Okay, now in the other case, where I don't reach t from y, or where I reach t, but after having reached x, yeah, okay, this is this picture here. Thanks to Thomas for making this animation. Okay, so in this case, I have got a cycle through the update, and that means that s cannot reach t, which means that the measure needs to get updated to infinite. Okay.
So only this method works even if there were cycles to begin with?
Yes. But what does it mean it works? So you see, no, you don't see it here. So this translation here is precise. So we have this property that I stated before. If I keep track of the measure in a precise way when I do destructive updates. Now, the funny thing is when I do non-destructive updates, then I lose information. And that is because I need to introduce new measures. Namely, a measure not only on the program variables, but also measures of the form m of y dot next, comma t. Okay. So I will have those expressions on the right hand side, but then I don't keep track of those expressions. So they will be updated non-deterministically. Yeah. And this is how I lose precision. Yeah?
Could you just tell me what you mean by non-destructive update in this context? What would be a non-destructive update?
I meant an update of where you don't update the contents of the cell, but you update the stack variable. This is what I mean. I mean, it's true. Thanks for the clarification.
So for example, there is another location R that can reach S, right? Here, this measure needs to be updated in the update.
Yes, yes. So so this is now let me go. Yeah. So you see here, you'd see an example of a translation. So you see that when I have this update of x dot n by y, then I update all these. No, okay, no. Sorry. So your question is which measures do I update when I have a statement? Yes. Okay. So this depends on which measures I track. So there is a heuristic to track certain measures and not others. So for example, here, because the while condition is on the variables p and q, I will track the measures p and q. Okay, and then I do a kind of cone of influence computation to infer what other measures I need to track. But in this example here, I track only p and q, and this is just to give you a glimpse. So this heap manipulating program here with these two update statements is translated into this integer program here, where each of the update statements is translated to, in this case, only one update statement for the measure m of pq. But thank you again for asking this. So if there were other measures I would keep track of, then I would, for each update, I would have a simultaneous update of several measures. So it's quadratic in the number of program variables, but it is linear in the number of statements. Well, okay. Yeah, times the number of times the square of the number of program variables, yes. But the number of measures we keep track of is not large. So it is, I mean, if we keep track of 3 measures, then it's 3 times n if n is a number of, no, it's 9 times n if n is a number of program variables. Yeah? MPX. Yes. Now it turns out that not. So I will execute the algorithm in a second, and Thomas, why don't we?
I mean, they occur in the updates, but they are not actually. So those are the ones that are updated non-deterministically. So think of just in addition to the update of the MPQ, you have a non-deterministic update of all the other measures that occur in the program.
Yes. 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 So we don't keep track of any other measures than the measure MPQ. And although the other measures occur in the right-hand side in the conditions here, for example, m of p comma x, this is where we will lose precision because we throw away information about those measures. Yeah. And thank you, Thomas. I said that each update is translated to exactly one update on this measure MPQ, but I forgot all the non-deterministic updates to all the other measures which assign a non-deterministic value to the measure. Yeah. So, in fact, you would have not only this update, but you would also have the update m of p comma x is assigned star. Yeah. And this is always left implicit. Okay, so I presented the transformation which does the initial abstraction, and I will now explain how I refine this abstraction and how the algorithm executes. And I will simply do an example run of the algorithm and incrementally introduce the algorithm. So the first step of the algorithm is to do this translation. Yeah, so the measure program PM is obtained by the translation of the heap program PH. So PH is the original input program with respect to a set of measures M. Those are the measures that we keep track of, and in this case, it's just the singleton. And I have here a loop that I will repeat forever, and I will extend the body of the loop while I'm going to incrementally explain the algorithm. So I will first check this integer program for termination with one of my classical termination analysis. And if this here terminates, it is a sound abstraction, then I'm very happy. I have succeeded my termination proof, and the precondition is true. Yeah? It will always terminate. Otherwise, and the second case is more likely because every termination of a heap manipulating program needs some reasoning over heaps, and it needs probably the correctness needs preconditions over the heaps. So otherwise, I produce a counterexample. So I take an infinite path, and now I will do something. Okay, so the infinite path is the one that simply, so intuitively you can imagine that it simply assumes that the measure MPQ is infinite. And the measure MPX is infinite as well, so it updates this measure according to the first case. So it will assign infinite, so it will not change its value. And then since the value is infinite, it will again assign infinite in this case, which corresponds to the translation of the update of x. Yeah?
The classic technique that you're using as a subroutine guarantee that when it produces an infinite path, in the abstract program it's guaranteed to be a non-terminating path?
No. You mean in the concrete program?
I mean, in the program PM, right?
So
What if the classical analysis also screwed up, right?
I mean the termination of integer programs is undecidable. Yeah. So I here assume that I have a very good termination analysis, so I don't worry about this part, right? So I said before that I use results of two recent lines of work. One is on termination analysis, one is of shape analysis, and I mean these tools are very good. They're performing very well, and the bottleneck is simply not there. The bottleneck is really when we want to combine them to solve termination of heap manipulating programs. Okay, so let's assume that the oracle, if this program does not terminate, then it will produce us a counterexample. I mean, termination is not even semi-decidable, so it's theoretically, of course, it's not clear that this works. So we have this example that takes the statement L0. So it simply assumes that that P and Q are not aliased. Then it executes the first statement according to the first case. So this is here the bracket. And then the second statement at the location L2, also the first case, and that it will iterate forever. Okay, so what will we do next? We will, I said I will replace this try something else, and I replaced it by this here. Okay, so I chose an infinite path, and in this infinite path I will choose a position, and in this case it will be positioned right at the entry of the loop here, and I will look at the guard of the corresponding statement at L2, and the guard is that the measure of PQ is infinite. Yeah? And here I use this double life of these measures. Here the MPQ is an integer variable, but I can use it as an expression in the heap program. So this assertion here can also be interpreted in the heap program. So I will insert it into the heap program and check the assertion. Yeah? And for this I will use my second tool. So in our case we use Bohne, which is Thomas' tool, which I mentioned before is optimized towards adapting the abstraction towards the task of proving one specific invariant. And here it is the invariant that the negation of the guard is always valid when you come to the program point L2. Yeah, so what does it mean in terms of the heap? It means that Q is reachable from P. Yeah. Okay, and Bohne will tell us that, so this is the guard, and the negation is that it's smaller than infinite, so that Q is reachable from P, and there is no reason that this should hold true. So Bohne will say no, the assertion is not valid. Okay, the program with this assertion is not safe. Okay, if it was safe, then what would we do? We would now use the negation of the guard, which was an assertion on heaps here. We would use it as an assertion of the integer program. So you would transform the assert into an assume and add the assume to the measure program, and this assume refines the abstraction. So this is how the abstraction refinement works. Yeah? So one could say an invariant that is implicit in the heap program will be made explicit in the measure program. And something we make explicit then refines the abstraction, and since it is true in the concrete, the abstraction is sound. So this is a very simple way of refining an abstraction. So it's something else than predicate abstraction, and it is, in a sense, it is poorer than predicate abstraction, because I add information only at one specific program point. Okay, but in this case, the assertion is not true. So we will try something else. And what is that? So look at once more at this program here. Obviously, we need as precondition that Q is reachable from P. Yeah? So if that is not the case, then the loop will simply not terminate. So I made another assumption, which is that the next field is interpreted as a total function. So I don't distinguish between non-termination and abort. Yeah? So if Q is not reachable from P, then I will have non-termination because at some point I will loop forever. Okay, so what is this? Try something else. We will now add a precondition. So the implicit precondition is true, and now we will refine the precondition. So in fact, always we check termination under the precondition. So the precondition is the measure assertion. So we can add it to the measure program. So we check termination of the measure program under the precondition, which is also a precondition on integer variables. And similarly, another addition is that we check the safety of the assertion that we added under the precondition. So the precondition is used in the analysis in two ways. For the termination analysis, because we need the precondition to infer invariants and to infer the termination. And also we use it in the shape analysis because every additional invariant that we have will make the shape analysis more efficient. Okay, so how do we strengthen the precondition? In a very simple way. We simply add exactly what needs to hold as precondition so that the assert is safe. Yeah? So, and when is the assert safe? When I add the weakest precondition of what I have asserted. Okay, so this is very trivial. So in this case, I need to assert that at the program point L1, I want that it holds true that at L2 I can reach P from Q, and this is why at L1 I need to assume that I can reach L from Q. Okay, and this I add now as a precondition. Okay, so if I reach Q, so precisely this means if I reach Q before reaching X, then I must be able to reach Q. Now we continue, and I think that I should. How much time do I have?
Well, we have the room until 12:30, but should wrap up in 5 minutes.
And I started 5 minutes late, right?
Yeah.
Yeah. Mm-hmm. Yeah. So I will not go through all the iterations of the algorithm. So this, what I described before, is now repeated. I find so I check termination under the refined precondition. I find a counterexample. I check whether the counterexample is due to the cause abstraction or because the precondition was not strong enough. And so either I refine the abstraction by adding an assume statement, or I refine the precondition by adding yet another conjunct to the precondition, and this conjunct is the weakest precondition of what I need to assume. Okay, I will go very simple through this, and yeah, and so here is the precondition that we compute, and this precondition is the weakest precondition for the Heap program. So this is really where we did not lose any precision. And I won't go, or maybe I can, no. I won't go through this, but it expresses the information on the shape that I need in order to have that this program here terminates even after the update of the cell referenced by x, the next field of x. Okay, so here is the full algorithm. I repeat all over again that I check termination of the integer program. So I call here a termination analysis for integer program. If this termination check fails, I don't know whether it's the cause abstraction or the too weak precondition. And I check the first. So, no, yeah. So I check whether the counterexample was spurious. And this is when some transition in the counterexample could not be taken because, in fact, the negation of the guard of one of the statements is an invariant. So that statement was infeasible. And in this case, I refine the abstraction by adding an assume statement. And otherwise, I refine the precondition by adding a conjunct, which is this weak precondition. So in red, you see the 3 oracles that I use, right? And for each of them, I have good machines. So here's the termination analysis for integer programs, and the other 2 is done by shape analysis. Okay, so I have we have a solid theoretical foundation for this algorithm. So there is a class of programs that I call regular, where the termination depends only on the shape, so on the truth value of the measure assertions. And in this case, the algorithm computes exactly the weakest precondition. And this algorithm always terminates. So I gave a non-deterministic control strategy, but you can choose one such that the algorithm terminates. Okay, so now I will wrap up. So I always hate if nobody has a question after the talk, so I will ask questions myself. And excuse me? Okay, but these are the questions I like because there's a good answer. I do a short summary. I talk about what we're doing now. And then I tell you that you can forget everything except for one thing. Okay, so the first question is, have we omitted the case when all the guards are in fact reachable, but in fact the infinite counterexample is not feasible, right? Because I only checked whether the negation of one of the guards is an invariant. And this is a very strong case, because even the finite path might still be feasible, right? Because you can reach from somewhere else. But still, I mean, this is what we did, and it works in practice. So I should have mentioned that we have a running prototype, a tool that's called Heap Infer, and that seems to work pretty well on practical examples. And also in the case where the finite trace is feasible, but the infinite is not, then this means that a ranking function based on measures does not exist. And this is then out of reach for our approach anyways. Then is the only refinement the deleting of these guarded updates from the integer program? Yes, almost. So it's a pretty weak refinement in a sense, except that these assume statements are also used by the determination analysis of the integer programs. Then is the approach specific to termination? No. But we did it for termination because in the other cases we have tools, right? So, and the last question, we call these 3 oracles, and do we make the problem easier by making appeal to 3 oracles for undecidable problems? Well, theoretically not, but practically yes, because we have great tools that work for these oracles. Okay, so what did we do? I think we gave the very first algorithm that infers precondition for termination for heap manipulating programs. This algorithm works by doing an initial abstraction that doesn't do any shape analysis or reasoning about shapes. And then we call shape analysis lazily, namely for each single counter example, we ask to delete this counter examples. And then we have this concept of the measure assertions, and they have this double life for the heap programs and for the integer programs. And then the last point, and this is what I want to talk about, this is what you can take away from this talk, even when you're not interested in termination analysis, but you're interested in program analysis. We came up with a scheme, which is not CGAR, but CGAR. The A is missing, yeah? Which is for refining not only the abstraction, but also the precondition. Okay, I skipped the ongoing work. So what do I mean by this CGAR scheme? So tools, usually they prove correctness under a given precondition. And then everything depends on the quality of the abstraction. If the abstraction is not good enough, then we have don't know answers, right? And the better the abstraction is, the better the analysis in the sense that we have less maybe answers, less don't know. And so there is this, to characterize these two extremes, right? So the greatest precision is model checking, where you don't do any abstraction, and then in program analysis you always do an abstraction, probably a rather coarse one, and there is this nice joke by Patrick Couzeau. I already told it a couple of times. So you know it? Yes. Okay, so I'll tell it in private then.
What's the joke?
Okay, so so if you call a model checker, you wait, and the model checker runs out of space, doesn't return. If you call a program analysis tool, it returns immediately and says don't know. Okay, and now here we propose something else than using abstraction for proving correctness under a given precondition. Namely, this is to infer the precondition. And now, the better the abstraction is, the better will be the precondition in the sense that it will be weaker, right? The weaker the precondition, the better, because for a greater set of inputs, the program will be correct. So in the worst case, for the most stupid abstraction, we will just say the precondition false. That's a sound answer. It's not that useful, but it's an answer. And in the best case, and this assumes that we have the correctness of the program, so this is when we have sufficiently good precision, then we will return true. And what we propose here is the CGAR scheme. So where we first try to make the abstraction finer and finer and get a better and better precondition, but after some time we run out of whatever, space, time, and whether we do it manually or automatically, we no longer want to refine the abstraction, and what we then do is we refine the precondition. Okay. In any case, we do this on demand. So in any case, each time we do this refinement, we eliminate the given counterexample, and we just don't know whether the counterexample was spurious or a real concrete one. But it doesn't matter. When we have stated, when we have refined the precondition, we have eliminated. Okay, and so this is a poor man's alternative. So when you have only a weak abstraction, two don't know answers. Right? So any precondition other than false is more useful than a don't know answer. That was it. Thank you. Mm-hmm.
What's your article for termination of integer programs? What do you use?
It's Andrey Rybalchenko's tool. So it's ARMC Live. So it's an implementation in Prolog.
So it infers these measure functions, tries to infer measure functions out of
So it infers these, we call them rank functions. Yeah. So then it infers rank functions. And so this is one thing. If it says that we need m of p comma q as a rank function, then the first thing that, so a rank is always a positive integer. In particular, it's different from plus infinite. So the first thing that we then add as an assumption is that q is reachable from p. So the measure of pq is smaller than infinite. So this is the first thing. This is the information that we get from Andrey Rybalchenko's tool. And then Thomas' tool checks whether p is in fact reachable from q. Mm-hmm. So the logic is really simply conjunctions of those arithmetic statements on measures. So either the measure of pq, where p and q are program variables, is equal to infinite, it's equal to an integer, including 0, and their negation. So it's not a logic, right? It's just conjunctions of those basic atomic measure assertions. Well, we don't have quantification. We don't have. No, I'm not. No. I'm not sure I understand the question. Why do you call this a logic? I mean, these are.
So actually, I have a similar question. So, keep history, so do you ever get non-unit coefficients in your expressions? So you were using the partial order, or you have some relation, reachability relation, and you're reducing that to arithmetic. But is that the full linear arithmetic, or integers, or reducing?
So for the assertions that I add to the Heap program, or that I add as assumptions in assumes to the integer programs, I have just the coefficient 1 on these measures. So it's always of the form measure of xy is equal to something or greater to something or smaller. And I'm not sure I understand your question. I mean, the ranking functions that are produced to check the assertions.
Which one, the termination solver or the other one, the Heap solver? He's making queries to two of them.
So, I mean, for the termination analysis, these are just simple assume statements on integer variables. And then the termination analysis tool that we have returns linear ranking functions. But the result of the termination analysis that is fed to the algorithm is not the ranking function. It just states this program is terminating or it's not. And as I said before, the only information that it gives back is which measures must be strictly smaller than infinite, right? So. Uh-huh.
But on the slides, they were even weaker. Yeah, right.
Mm-hmm.
still, and this is related because that work is a clear connection to logic, topology, etc. So I don't know if you're aware of this work. It's not directly connected to this, but there might be some connection here.
Yeah. So it's in the context of complementation of Rabin automata, right?
Yes.
And
Proving lightness properties.
yeah, yeah.
Reasoning about infinite computation by looking at finite measures, quantitative measures.
But I think that yeah, this is in game theoretic reasoning, which is not at all what we have here. So I mean we called them measures because we found that it sounds much better than counters, right? So Bourjani and Byron Cook called them counters, but but I admit that there is this connection to measures, and that's perhaps a misleading connection. Yeah. And perhaps coming back to your question, so these measure assertions, for example, m of p, q is smaller than infinite. This translates to q is reachable from p, which can be expressed in monadic second order logic. Do you mean this logical connection? Mm-hmm. Yeah.
This tool, the ARMC tool, the termination analyzer, why does it take as input only an integer program? What is the problem with making it work on just an arbitrary program? Is it some heuristics issue that uses some heuristics that are tailored towards integer programs? In other words, why termination of any program, doesn't matter whether it's integer or not, they're both undecidable and grossly undecidable. So why is there this restriction that it should only take an integer program as input?
Because the termination analysis works by constructing a ranking function.
Okay.
And so this is a function into a well-founded domain. So one can always take the natural numbers as the domain. And that's isomorphic, but that's always the domain that people take.
Okay.
And we just don't have any termination tool that constructs ranking functions other than those that apply to integer expressions and return integer ranks. Yeah? So where the set of ranks comes from the set of natural numbers.
I mean, but for example, if you take C, right, every variable and every expression in a C program does return an integer. You can think of a C program as an integer program, right? So why not? I mean, for example, you have this unbounded heap.
Mm-hmm.
You can think of every address as an integer.
Yes. But I think that thinking of a heap in terms of a function from integers to integers is not it's not a good idea. I don't know any tool that reasons on heaps in that way. Do you know, Thomas? It seems to be too low level. That's true. The sequences that I use when I do the dereferencing, it does not at all obey to the order of the integers, right? Because you can jump in the, well, can you jump in? Exactly, yeah. So it might, I mean, in fact, I said integers, but we use a solver over rationals, yeah. Really, that's true, yeah.